Dear students, I welcome you for the today's lecture related to the heat exchanger designing numericals. So first numerical that we will discuss, suggest a suitable design for a condenser to be used for condensing 4.2 kgs per second of steam. That means we want to condense the steam. Its mass flow rate, that is 4.2 kgs per second, is provided. The steam will be condensed at a pressure of 413 kilonewton per meter square, and steam has a dryness fraction of 0.92. So the steam, it is having a dryness fraction of 0.92. Cooling water is available at 17 degrees Celsius, and for economic reasons, the temperature rise has to be limited to 6 degrees Celsius. So inlet temperature, maximum temperature is 17 plus 6, that is your 23 degrees Celsius. Water velocity that can be used for the purpose is limited and maximum up to 1.2 meters per second through the tubes. Here the water velocity, water flowing through the tubes, is having the maximum velocity of 1.2 meters per second. One has to understand the operating range of the fluid velocity through the shell side as well as through the tube side. Here the tube side water velocity is around 1.2 meters per second. So in the tubes, one can generally go up to 2 to 3 meters per second, not more than 3 meters per second. If it is more than 3 meters per second, then there can be the higher pressure drops that will take place, and which is again becomes not economic issues will be there. And for very low velocities less than zero point 0.1 or 0.5 meters per second, there will be no turbulence, Reynolds number will be very low, and again the heat transfer coefficients are less. So G generally 1 to 3 meters per second is the tube side velocity, and for shell side it is around 0.5 to 1 meter, 0.1 to 1 meters per second is generally the velocity on the shell side. The exchanger has two passes on the tube sides to maintain this much velocity. Tube OD 19.05 millimeter, tube ID, that is 15.55 millimeter, can be used. Estimate the number of tubes, how many number of tubes that will be required, then the tube bundle diameter, the shell diameter, and the heat transfer coefficient based on the external area of the tubes is given as 3400 watt per meter square Kelvin. So this much data is given, and in this numerical it is expected to calculate the number of tubes, tube bundle diameter, and the shell diameter. This is all about the exchanger layout. This problem is focused related to the exchanger layout. However, the diameter of the tubes that is mentioned. So the other material that is provided density of cooling water, steam temperature at 4.13 kilonewton per meter square is 29.5 degrees Celsius. Latent heat of vaporization is 2430 kilojoules per kg. Then the dryness fraction for the steam is 0.92, that is what is provided. So the specific enthalpy of a wet steam vapor. So latent heat into the dryness fraction, this much amount of the heat that is to be removed, 2235 kilojoules per kg. So specific enthalpy, that is what, this much amount of the heat has to be removed to convert 1 kg of wet vapors to the 1 kg of saturated liquid, and its flow rate is mentioned as 4.2 kgs per second. So the total heat with this flow rate of 4.2 kgs into the latent heat into the dryness fraction will give you the total amount of heat that is to be removed from the steam. So this much amount of the steam is to be removed with the help of a cooling water. So I can calculate the cooling water flow rate by considering this heat upon mCp delta T or WCP delta T. So that comes as 337.76. Then the volumetric flow rate upon the kgs per second divided by the density. 995 is the density kgs per meter cube that is given. So this is kgs per second, kgs per second divided by kgs per meter cube density, which will give you the volumetric flow rate. Then once the volumetric flow rate that is known, then the total number of tubes required are to be calculated. So total number of tubes, and here the two passes are provided on the tube side. So number of tube side passes are 2. So cross sectional area of one tube, that is pi by 4 into di squared, and the flow area per pass. So n number of tubes divided by the 2, that is in one pass. So ACP so number of tubes, that is equal to total area upon the calculated outside surface area of the one tube. So here the cross sectional area, the fluid velocity, fluid passing through that tube, based on that we are calculating, that is the cross sectional area of the tube, that is pi by 4 di square upon the flow area per pass is the area into total number of tubes divided by the tube. So volumetric flow rate of the water, that is the flow area per pass into the velocity. So you are having the volumetric flow rate as 0.3756 meter cube per second, 0.3756, and the flow area, that is cross sectional area, that is 1.887 into 10 to the power minus 4 upon 2 into the n into the velocity, that is 1.2 meters per second. So total number of tubes that are calculated around 3320. Then the log mean temperature difference, LMTD, temperature gradient that is mentioned, 29.5 degrees Celsius is the temperature of saturated steam. Steam temperature at 4.13 kilonewton per meter square is 29.5 degrees Celsius. So 29.5 degrees Celsius and the 17 degrees Celsius log mean temperature difference. So this is the temperature curve for the steam, and the slight temperature increase that will be there. So it is 17 degrees Celsius and the outlet temperature, that is 23 degrees Celsius. So temperature difference at this and the temperature difference at this end minus temperature difference at the another end. So your log mean temperature difference that comes as 9.17 degrees Celsius. Then the heat transfer surface area required, which is Q, which is equal to UA delta Tm, where Q we have already calculated as the 9389, U that is 3400, U in this case that is assumed to be the 3400 because it's a steam and the steam is having the higher heat transfer coefficients. If it would have been water, then the heat transfer coefficient is around 1000. However, when it's a steam, condensing steam, and the water on another side, its heat transfer coefficient is around 5000 or so. So we are taking, or from past experiences, the heat transfer coefficient is assumed to be 3400 watts per meter square second. It is based overall heat transfer coefficient based on the external area of the tubes, that is 3400 watts per meter square Kelvin. And delta Tm log mean temperature difference 9.17. So this much area you will get. Now this is the pi do, the outside surface area of the tube per meter length. This is per meter length. So surface area pi d into the L. So it's a per meter length we are calculating. That is for pi d into the 1 that is taken into account, and the pi and do, the outside diameter, because we are calculating here the heat transfer coefficient area based on the outside surface area, and that is why we are considering this area, calculated area, as the outside area, and so we consider this outside diameter do. So let the length of the each tube will be is equal to L meters, and so from this much area and this much number of tubes I can calculate the length as 1.52 meters. So assume that the tubes are arranged in a square pitch. Now this is one assumption we are doing. The tubes are arranged on a square pitch arrangement. Now the calculation of the tube bundle diameter can be calculated as dB, which is equal to the do into n upon k raised to 1 upon n. So where the k and n, they are the constants depending on the square pitch arrangement. So these two constants, they are already provided, and dB, which is equal to the do into the capital N, which is the number of tubes, that is 3320 are the number of tubes, and k and n. So diameter that comes as 1.476 meters, and excess of 10% that is to be taken into account. So 1.62 meter diameter, that is 1.62 meter. You can now imagine this 1.62 meter diameter, that is more than 1 meter. So I can have the total area that will be there. Now the next numerical, that is this is the oil and water. However, this 1 kg of the fuel oil is to be heated by passing through a concentric tube heat exchanger. In this case, we are considering a concentric tube heat exchanger, and where temperature is to be increased from 10 degrees Celsius to 25 degrees Celsius by using the hot water available at 70 degrees Celsius. Means fuel oil we are heating, which is at a rate of 1 kg per second. And the hot water is used. The water flows through the copper tube with a velocity of 0.76 meters per second. Now you can see the velocity here, 0.76 meters per second. In previous numerical also the velocity is 1.2 meters per second. That is in the tubes. Here it is in the copper tubes, again in the tubes. The oil passes through the annulus formed by the inner copper tube and the outer steel tube. Inside there is a copper tube and outside there is a steel tube, steel pipe which is available. So copper tubes are available and around that there is a steel tube which is available. So ID of the copper tube that is mentioned as 18.6 millimeter, OD of the copper tube that is 21.3 millimeter, ID of the steel tube that is 30 millimeter, and OD of the steel tube is 33.4 millimeter. The specifications related to the dimensions of the tube they are provided. Then the fouling factors on the water side is 0.0004 meter square Kelvin per watt, and the fouling factor on the oil side, that is 0.0009 meter square Kelvin per watt. And the copper wall resistance can be neglected for as when we will calculate the overall heat transfer coefficient. This copper as the material is copper, so you can neglect because of the higher thermal conductivities. And the data provided for Cp, thermal conductivity K, viscosity and the density for both oil and the water. So the water that is flowing through the tubes, the hot water. Now coming to the designing steps for the shell and tube heat exchanger, that is we first consider the heat load by considering the mass flow rate and the mass flow rate for the hot fluid and cold fluid and the inlet and outlet temperatures for the hot fluid and cold fluid, out of which the temperatures they are already provided, the flow rates they are already velocity that is already provided and the flow rate that is already provided. Then the physical factors or physical properties, that is viscosity, density, Cp and thermal conductivity, they are provided. In this case the type of exchanger is a double pipe heat exchanger that is used. Then the calculation of log mean temperature, calculation of the area by considering the overall heat transfer coefficient, then the exchanger layout, calculation of individual heat transfer coefficient HI and HO, then calculation of UO, overall heat transfer coefficient, and then the calculation of the delta P, and finally optimize the design. So the heat transfer by water, which is mCp delta T, m that is the 0.76 is the velocity that is mentioned, meters per second, into the density, 982 is the density of water and 0.76 is the velocity of copper tube, velocity of the water flowing through the copper tube, into the area, into the cross sectional area of the tube. So we are considering here the ID, diameter, inside diameter, that is pi by 4 into the inside diameter. This is velocity into area, that will give me the volumetric flow rate. This is meters per second into the meter square, and this is having the units of kg per meter cube. Kg per meter cube. And this is the Cp and this is the delta T. The outside temperature of the hot fluid that is not mentioned. So heat loss, which is equal to heat gain, we can calculate the heat lost, that is by considering the mCp delta T, that is the mass flow rate for the fuel oil, m, Cp is mentioned here 1884 into the delta T of 15 degrees Celsius. From there I can calculate this as the heat gained and the heat lost. From here I can calculate the MCP delta T for the water, which is equal to the MCP delta T for the oil. So outlet temperature, that is calculated as 36.7 degrees Celsius. From there I can calculate the LMTD, log mean temperature difference. That is from 70 degrees Celsius to 36.7 degrees Celsius, and water that will flow from 10 degrees Celsius to the 25 degrees Celsius. This is 25 degrees Celsius water, and this is the 70 degrees Celsius, that is for the hot fluid temperature. So LMTD that can be calculated. Then coming to the exchanger layout. In the exchanger layout, it is already mentioned that the ID of the tubes, OD of the tubes, that is already mentioned. So in this case, it's a double pipe heat exchanger. So only the tube dimensions, that is diameter, thickness and length, that will be of consideration. However, the pitch arrangement, that will not be considered. Then decide the number of passes, calculation of outside surface area, that calculations can be there. Then the number of tubes, that will not be there. Bundle diameter, the diameter of the shell and the baffle spacing, that will not there. So directly coming to the individual heat transfer coefficient HI. So first we have to consider the cross sectional area of the one tube, which is the pi by 4 into di square. Then the number of tubes per pass NP, which is equal to the number of tubes, total number of tubes upon the tube side passes. Then next is total cross sectional area in one pass on the tube side. Then the velocity of the fluid through the tubes, which is ut, which is equal to the mt upon acp rho t. Then the Reynolds number, Prandtl number, and calculation of the individual heat transfer coefficient, that will be there. So the Reynolds number du rho upon mu, where the di will be there. Ut is the velocity through the tubes, rho t is the velocity of the fluid through the tubes, and mu t is the velocity of the fluid through the tubes. In this case, the hot water, that is the passing through inside. So diameter, inside diameter of the tubes, di, the velocity of the fluid, that is the hot water, and the density of the hot water, that is mentioned, and the viscosity for hot water. So it comes as the 33,900. So it's a turbulent flow is there. After that, the Prandtl number that can be calculated, which is Cp mu upon K, that is all related to the hot fluid. So Cp 4180, viscosity and the thermal conductivity, that comes as the 2.608. A very small value of Prandtl number that is there, 2.6. Generally the around 1 to 5 is the value of Prandtl number, generally, if it's a water or other fluids also. Then the transfer coefficient water side can be calculated by the Dieters-Voltas equation. Nusselt's number, which is equal to 0.023 into Re raised to 0.8 into P R raised to 0.33. So individual heat transfer coefficient HI, that will be calculated as 4687 watt per meter square Kelvin. Next is the shell side heat transfer coefficient HO. The area of the bundle cross flow, that is the AS, which is nothing but the pitch into the DO into the DS, PT minus DO into the DS into the length of the baffle, that is DS is the shell diameter, LB is the length of the baffle, then the velocity of the fluid on the shell side, that is the U is the velocity on the shell side, which is equal to mass flow rate on the shell side upon the area of cross section of the shell side, area of the surface area for the shell side, then rho s is the density of the fluid flowing through the shell. Then you have to calculate the equivalent diameter dE, which is nothing but the cross sectional area of the flow upon weighted perimeter. Then calculation of Reynolds number, Prandtl number, and finally the HO, that is the outside heat transfer coefficient. So equivalent diameter in this case, that is Di minus Do, as it's a concentric pipe heat exchanger. So equivalent diameter that comes as 8.7 millimeter. Then the annulus area, that is pi by 4 into Di square minus Do square, that is the outside diameter, outside tube inside diameter, and the inside tube outside diameter. There are two tubes, that is one is the outer tube का inner diameter, and the second is the inner tube, so uska outer diameter. That means the area which is available, this is the annulus area, ये दोनों का area है, that is this annulus area. Then the Reynolds number in the annulus, that is the equivalent diameter into the mass velocity into the viscosity. So equivalent diameter that comes as the 8.7 millimeter, 0.087 into the mass velocity 1 meter kg meter square second. Then the viscosity, that is 0.35 into 10 to the power minus 3, and which comes as the Reynolds number as 3920. Then the value of the Prandtl number, that is Cp mu upon K, that comes as the 86.55. Then the annular flow heat transfer coefficient for the fuel, that can be calculated by using this equation, where HODE upon K, which is equal to 0.023 into RE raised to 0.8 into Prandtl number raised to 0.4. In this case, the fluid that is getting heated, and that is why inside fluid which is getting heated, the fluid which is outside the tubes will be get heated, because inside it's a hot fluid. This is inside it's a hot fluid, and we are doing this calculation for the annular section. So it's a 0.4, and this comes as the 1628 watt per meter square Kelvin. That is the outside heat transfer coefficient. Then the calculation of the overall heat transfer coefficient, in which we have to take into account the inside heat transfer coefficient, which is based on the outside surface area, UO, 1 upon UO. That is why we are multiplying by DO upon DI for the inside heat transfer coefficient, and DO upon DI for the resistance, or 1 upon HID dirt factor. So the Ri for the inner tube fouling factor is 1 upon HID. Then the RO outer tube fouling factor 1 upon HOD. And KT is your thermal conductivity of the tube material, as it's a copper. So this term that can be neglected. So we will neglect this term. So the remaining is 1 upon HI, DO upon DI plus 1 upon HO plus FWI plus FO. That is the fouling factor on the water side, fouling factor on the oil side. So the total UO that comes as the 463 watt per meter square Kelvin. Then the length of the heat exchanger, that is Q, which is equal to UA delta Tm. Q, that is already calculated for the fluid which is to be cooled from 10 degrees Celsius to 25 degrees Celsius. So that is to be already calculated. and U that is calculated is 463, in log mean temperature difference is 35. So area comes as 1.744 meter square. So area upon pi do into L, that will give me the length. Total length is coming to the 26 meters only. It's a not too much area, 1.74 meter square. It's a very low area, and that is why we are choosing this a concentric pipe heat exchanger. We are not going for a shell and tube heat exchanger in this case because the area is very small. So the theoretical length required is 5% excess in addition to account the heat losses. So length that becomes 27.3 meter. So concentric tube heat exchanger can be constructed with a 4.55 meter length in series, and 6 tubes in of 4.55 meter length are required. Then next is the calculation of pressure drop on the tube side. We are having the F, which is equal to 0.046 into Re raised to zero point 0.2, which we have studied in the fluid mechanics or the fluid flow operations. Then the second equation that is also there, 0.079 into Reynolds number raised to 0.25. So delta P in the tubes, which is equal to 4F L upon Di into rho ut square upon 2. That comes as the log mean temperature difference for the fluid, for the fluid flowing through the tubes. Then the tube length, velocity of the fluid flowing through the tubes, and the F is the friction factor. So the pressure drop, which comes as the 2F L rho u square upon Di, and the friction factor, which is 0.079 into Re raised to 0.25. So friction factor that comes as 0.00582, and delta P that comes as 9.69 kilonewton per meter square. Then the retention losses, rho u square upon 2, which is delta P, that comes as the 982 into 0.76. 982 is the delta P, which is equal to the H rho G. So 284 Newton per meter square is the return loss pressure, half mv square. There will be the 5 U bends in the exchanger. So the total pressure drop due to the bends, that comes as 1.42 kilonewton per meter square, and the total pressure drop through the tubes, that is the frictional pressure drop plus the pressure drop in the bends, that will be is equal to 11.11 kilonewton per meter square. And this much pressure drop is within the acceptable limits, and so the design that can be accepted here itself.